So, we turn now to the last paper, which is back in the foundation track, and it's going to be presented by Dennis Vagela from Brussels,
Yeah.
University of?
Free University.
Free University of Brussels. Okay, thank you.
Thank you very much, Colin. So this is actually a joint work between Free University of Brussels and École de Mines de Nantes. So there are a couple of more names on there. And it's going to be about an approach to general composition semantics for rule-based model transformation. So let me start off by giving some context here. As we all know, model transformations play a central role in model-driven engineering. And it's actually so that the complexity of model transformations has risen significantly over time. And that means that things like modularity, reusability and maintainability are starting to become important in writing model transformations. To illustrate this, many model transformations are already broken down into a chain of incremental model transformation steps. And that is actually already a form of composition that is sometimes known as external composition. And the advantage of that is that it's language independent, as long as we can pass models between these different steps. But it's also coarse-grained, in that each transformation step is executed as a whole or not executed at all. We can't influence parts of the transformation in that way. On the other hand, there's something called internal composition, which endeavors to compose multiple modules of model transformation into a single module before executing that module as a whole. So they were actually talking about model transformations as programs, where we try to compose it into a single program first. This allows us to do fine-grained overriding and replacing of parts of a transformation, such as rules that we want to swap out for other rules, where we want to basically reuse 90% of an existing transformation. But a very important constraint of this kind of composition is that the modules have to be expressed in the same language in order to provide a sound definition of what composition means there. So what we're trying to do is to mitigate that language dependency as much as possible and try to make composition mechanisms, internal composition mechanisms, that are portable across multiple transformation languages. And the reason for doing this is actually that we found out that different model transformation languages have different strengths. Graph transformations are very good for in-place style transformations, such as refinement, incremental refinement, or refactoring. And mapping style languages, such as QVT operational or ATL, are very good at doing a total translation of one domain to another, when there are simple mappings available. So we've seen that certain problems are simpler to solve in one language and other problems simpler to solve in another language. What we've also found is that the concept of rule is actually central. So we're trying to focus on that. A lot of transformation languages have a notion of rule. So that's basically our starting point. Now the way we want to achieve this general semantics is by using a virtual machine that's going to execute our model transformations. We have a bytecode for that, and we are able to translate or compile multiple transformation languages that have a notion of rule to this bytecode. Then we compose the homogeneous bytecode modules inside the virtual machine before executing them. So currently we have compilers available for the ATL language and a language called Simple GT, which is a minimal double push-out graph transformation language as a proof of concept. So these are already different in the sense that ATL is one of these mapping style languages that does one-shot rule matching and basically translates source domain to target domain. It doesn't do in-place transformation. Whereas Simple GT is a graph rewriting language that applies its rules recursively and can basically keep on rewriting until a fixed point is reached. And we've managed to come up with a common composition semantics for that. And let me show you how that works. We'll start from this picture. What sits actually in the bytecode is an explicit notion of module, that much is clear, but also an explicit notion of rule. And it's this two explicit notions that allow us to define common semantics for rule inheritance and module import. We can actually, we can use the metadata that we all have, that we have in the bytecode about modules and rules, to define how rule inheritance has to work and how module import works. So I mentioned them both because they interact with each other, as we can see later on. So that's basically that. We go a little bit deeper into the bytecode and what kind of virtual machine we're actually talking about. Basically, it's a stack-based virtual machine that processes lists of instructions, some of which are specific to model manipulation. So right now we have some 47 different instructions, so it's not that big of a virtual machine. The instructions are actually grouped inside code blocks. So the code blocks represent the lists of instructions, and they can serve as implementations of fields and operations, which is pretty much a standard notion. But they also provide detailed behavior for the rules. Here we have a matching code block, which basically evaluates whether a rule matches against a certain input or not. An applier code block that actually performs what the rule should do. There's a post-apply code block as well. That is if you want to make a second pass. That's mostly there for pragmatic reasons. Furthermore, rules have input elements and output elements, and rules can list a number of super rules by name. This is necessary for the rule inheritance mechanism. Actually, the rules are only linked at load time, so we can still change the actual rule. That's why it's a string here. Furthermore, rules have an execution mode. It can be triggered manually, they can be triggered automatically and only applied once, or they can be triggered automatically and applied recursively until a fixed point is reached. Rules can be abstract. That means you don't apply a rule unless a sub-rule will also match and trigger. Default represents what kind of traces are generated. So ATL has an implicit tracing mechanism and has this notion that every source pattern corresponds to a unique target. But in a rewriting language, this is not so clear, so we can't use the same kind of tracing. Distinct elements is another big difference between graph transformation and ATL. This basically says whether a rule that matches certain input elements matches all distinct elements, or you can match the same elements into slots. So that's all we need to know to get to the next part. And this is where I'd like to talk a bit about how we wanted to do rule inheritance. So we're supporting multiple inheritance here, as you can see, and we're basing ourselves on the semantics of ATL and triple graph grammars that both already have a notion of rule inheritance. So we take that as a starting point. Basically, that means that subrules, like this one here, will only match if there is a combined match of all the superrules and the subrule together. So the superrules have to match first. Also, if the same identifier is used for a certain input element, then all these identifiers must point to the actual same model element. So here we have AT, which occurs 3 times. When there's a combined match, this AT element must point to the same model element to produce a combined match. So let's see in a bit more detail how that's going to work. So if we are going to produce a combined match, it could go like this. You have the rule class that matches an element CL, which is a class, an element AT, which is an attribute. Then this rule index here matches an A, which is an annotation, and an AT, which is an annotated attribute. And we actually find out that for some matches, these ATs are the same. So then these are a combined match already. And then we can look at the rule key. Key also matches an AT, which then has to be a key attribute. If it is the same element as these ATs, we actually have a match. And we have to also find a KA, which is another annotation. So actually, what goes on is that the rule key inherits all the elements that aren't listed explicitly here from its super rules. So it still matches a CL, and it still matches an A element, even though they're not listed. So we can also apply these rules in combination. We'll look at that later. What is a fact here is that in terms of lexical access, this rule cannot refer to the elements that it did not repeat here. So it can only refer to AT and KA in order to specify what this rule should do. So this is done so that we can later reconfigure or replace rules in the hierarchy without creating fragility here. The application semantics are a bit similar here. Actually, this is part of the rule application phase, which is when all elements are created, and then we have a look at how they are created. So basically, they follow the semantics for matching as far as these identifiers are concerned. So the CO element here, they all have to point to the same element. And the rules for instantiating output elements are as follows. You take the type from the most specific rule in the hierarchy. So CO is instantiated as a key column, and TB is instantiated as a key table. And they're also specified here under different types. So that means something. That means that we have a covariance constraint here. That key table actually has to be covariant with table, has to be subtype or similar to table. So we can safely replace the type with table. And the same goes for keyed column. Keyed column has to be subtype of index column and of column in order to safely use the same element in these rules. So this is something to keep in mind. Here we actually have some safety rules regarding types. Now there are different application strategies or algorithms, if you will, for applying the different kinds of rules depending on their mode. So manual rules, that's the simplest case. They're triggered explicitly from the bytecode, so you really invoke them by name and you pass the input elements as parameters. And then basically they just inherit the behavior of their super rules that are also manual rules. Automatic single rules, they're applied automatically, and there's an algorithm to go with that. So that's what I'll explain right here. The first step is to match all the rules that don't have any super rules. So that's a really simple case. Then we just store the matches for later use. So now we have each rule that triggered and then the tuple of input elements on which they triggered. Second step is to continue on that and match all the rules for which the super rules have got any matches. And we're actually matching on the previously matched data. So this is how we ensure that we don't start matching any rules for which the super rules haven't yet been processed. And in case there is a match of a sub-rule, we basically override the super rule match and we store the sub-rule match instead. So the step 3 obviously is then to keep on doing 2 until we've gone through all the single rules. And in the end, we're ending up with all matches over all the rules. So what we can do then is create output elements for all these matches and convert the matches to traces, where we can say, okay, these are the output elements that go with these input elements. And once we've done that, we can apply the rules for each trace starting from the super rule. So that means that sub-rules can override the behavior, the application behavior of super rules. And rules are applied also in the inheritance order in which they are specified, depth first, if you want to know. Then there's a post apply that basically follows the same strategy. So post apply allows you to do a second pass after you created your model. Same thing, as for applying also counts here. So it's same strategy. Automatic recursive rules, they follow a different process because they're actually used to do in-place transformation and rewrite and possibly change their own input. That means that if you record any matches and you apply one of these rules, you may invalidate any previously recorded matches. So you have to restart matching every time you change your input in order to be safe. So there are certain ways around this, but we do it like this. So it starts off the same. We match all the rules that don't have any super rules. We store all the matches. If these rules have sub-rules, But if this is a rule without a subrule, we just store the first match. There's a reason for that. If one of those rules, a non-abstract rule, without any subrules matches, we know we don't have to continue because there are no subrules. So it's actually really this rule that has matched. So then we apply that rule all the way, apply and post-apply, and then we restart the algorithm. If this doesn't happen, then we just continue, and we start matching rules for which the super rules have matched on the match data that we found before. And we again store all the matches when more subrules exist. And otherwise, if we find a leaf rule, we store the first match and we do the same thing. We apply that rule and we just restart the entire algorithm. Now we keep on doing 2 until we've processed all the rules. Let's say that happens. And if we then arrive at the end, we've gone through all the rules and we haven't found any match of a non-abstract rule, then we end the algorithm, and otherwise we take the first match and we restart the algorithm again. So this is basically a loop in a loop, if you can see it. So now we know a bit about rule inheritance. Now let's look at module import. Basically, module import is a construct that most model transformation languages already support. It's very basic. So the difference here is that we align module import with rule inheritance. And for that we first need to understand how rules, operations and fields are stored, or rather registered, inside the VM. So they all go in a lookup table. Rules are stored by name. So if I look up a rule, it's just by name. Operations and fields are stored by signature. And a signature basically consists of a context type, name, and a number of parameter types. So just to keep that in mind, now we can discuss how module import works. Module import effectively defines the order in which we're going to load and therefore register the rules, fields, and operations. So modules are imported depth first. So and they're actually always a module will also always load its imported modules before it loads itself. So yeah, here's an example of how it works. Here's a module M1 that imports M2 and M3. So let's start here. We're not loading M1. First we have to import M2. So here's M2, which imports M4 and M3. So we wait with loading M2 and we start loading M4, which doesn't have any imports. So this is just loaded and we're done. Now we have to import M3. Here, this one wants to import M4, but we had already loaded that. So we don't have to do that anymore. Now we've loaded M3, we load M2. We go back to M1, wants to import M3, but that we've already loaded. So this is done too, and finally we load M1. So this order of importing allows for each module that specifies imports to have a chance to overwrite, or rather overwrite in the registry table, what kind of rules you want to have active in what kind of fields and what kind of operations. So let's consider what that means. So for replacing fields and operations, we're actually pretty safe with regard to types because we store them by signature. So we only replace fields and operations by fields and operations with the exact same signature. For rules it's not the same because they're actually registered by name only. So again we have to enforce some safety constraints here, that rules should only be replaced by exactly the same type of rule. So manual or automatic, single recursive, distinct or non-distinct elements, default or non-default. So the reason why we only store them by name is because otherwise you get really complex inheritance statements that require much more than just the name of the super rule. So we want to keep it simple and we just constrain this. Also, apart from that, when you replace a rule that is exactly the same kind, it should not break the rule inheritance safety rules with regard to the covariance rules of the output elements. So this is also something that you need to check at the moment you've done your module import. So those are basically the composition constructs. Now we're going to illustrate briefly how we map the model transformation language to this bytecode. So this ATL, to start with, actually ATL has a couple of key constructs that I'll discuss. It has source models, it has target models. Source models are read-only, target models are write-only. They map to input and output models inside the VM. And this allows us to use that algorithm that I showed before, that we can do a one-shot matching, because it won't affect, the matching won't be affected if any rules are applied. So also the key construct in ATL is a matched rule, and that translates to an automatic single rule in the bytecode. The rest I will skip for now. Then our other language, that's our double push-out graph transformation language, simple GT. The key constructs there are simply a model, because we're going to do in-place rewriting on that model, and a rule. And what we mean by rule is actually more specified if we translate it to the bytecode format. It's an automatic, recursive, distinct rule. Because here we're matching distinct input elements. We mentioned 2 nodes in our input, our matching graph, then we actually mean 2 different elements. A model is an in-out model. We can read from it and we can write to it. So that's basically that. I have some time, so I'm going to show you, because ATL is fairly well known, but simple GT is just something I made up. So I'm going to show you a short snippet of code that explains what simple GT looks like. So again, it's organized in a module. It transforms a model, which in this case is a graph, and then you have rules like this. So rules, there can be abstract rules, there can be actual normal concrete rules. You have rule inheritance here. So what this transformation does is it tries to reverse all the edges. It also shows that I need to do something extra when I have recursive rules that run to the fixed point. I need to create this marker here, which is a trace source element. Doesn't matter what it is. It's a marker that shows that I've already been there. I've already reversed this edge. So I'm trying to match here that I haven't reversed it yet, and here I'm creating the marker to reverse it. And there are actually 3 sub-rules of this that cover the 3 different cases. A fully connected edge, an edge that's only connected at the source, and an edge that's only connected at the target. But they all inherit this behavior where we try to find the marker or create the marker. So, time to conclude. So we've presented an approach for a general composition semantics for rule-based transformation languages, which is based on a model transformation virtual machine, the EMF Transformation Virtual Machine, we called it. Basically, the VM provides a low-level bytecode language to do EMF model manipulation. High-level rule-based transformation languages are then compiled to this bytecode language. So currently we have support for ATL, which is a mapping style language, and simple GT, which is a rewriting style language, which goes to show that we can actually find a common notion of rule inheritance for different meanings of rule. The composition is performed inside the VM on actually homogeneous bytecode. And what makes it possible to do this is to actually have an explicit notion of rule and module with all the metadata that we need in order to perform the composition. And this is actually different from the model transformation VMs that already existed out there. They compiled all this metadata away, so we couldn't safely do composition anymore. As an outlook, currently the rule inheritance only works between rules of the same kind. So we've only investigated how it works for, say, manual rules, automatic single, automatic recursive, default or non-default. So what we actually want to do in more detail is investigate possible semantics for inheritance, rule inheritance between heterogeneous rules. And that we have to investigate in more depth. Also, we don't have support for synchronization style languages, as I will call them for now. Such as triple graph grammars of QVT relations, which have something like match this output, and if it doesn't exist, otherwise create it. So if you actually try to encode this in a rule that will always create elements, and that will just have to match source, you have to create many rules to represent a single of single triple graph grammar rule, for example. For each output element that you create, you have to check whether it first exists. So that kind of explodes, and we don't have a nice way to map that yet. Also, because EMF Transformation Virtual Machine already implements the entire ATL and simple GT languages, it could serve as a general transformation language interoperability solution for model transformation based on EMF. And in fact, we're going to do another experiment with EMF Migrate framework, which includes domain-specific model transformation language for migrating transformations based on one meta model to an evolved meta model. So here's an experiment that we're already going to try and use this as a common EMF manipulation runtime. That's basically it. If you want more information, these are the websites that will have more information. This VM will become part of ATL. It's already in Eclipse, so eventually if you get ATL, you will also get this VM. So are there any questions?
Yes.
How does the performance of your VM compare to, for example, ATL?
Right now for ATL rule semantics, because you saw two algorithms. The algorithm basically follows the same strategy as the ATL VM, so it scales the same. Performance-wise, it's right now also on par. We did a few extra tricks in this virtual machine. We did multi-method dispatch that the original virtual machine doesn't have. And yeah, we have multiple inheritance as well. And what do we also have? Yeah, we work with closures. So we have a higher order implementation of OCL collections. And original ATL flattens these higher order functions. So we're right now on par. As for graph transformation, we're quite a bit slower, I should say, because it turns out to be a bit inefficient to do your rewriting directly on EMF. So EMF is not so lenient to rewriting. So there, it is, in order to optimize that, it's a very good idea to find an optimized representation of your graph. So, which is probably something you already know.
Yeah.
Did you investigate the use of other model transformation languages which were intended to be interoperability formats? I mean, that was the original aim, for example, of QBT, was to be an interchange and interoperability language for transformation. So did you look at using those? And were there specific reasons why you didn't use, for example, SQL or something?
Yes. I've been discussing that issue as well with Ed Willink, who suggested OCL primitives. This is mainly. I first wanted to do something really pragmatic and start off from something that works. So I basically borrowed the architecture of ATL that has been proven, and then I learned a couple of things about compiling to bytecode. So actually, if you want to write a very simple compiler, it would be nice to have more or less one-on-one mappings where number of elements on the right map to exactly one element on the left-hand side. So I saw that if you use something like an expression language, a language that has a notion of expressions already, those expressions have to map exactly to one or a number of input elements. If this mapping isn't very exact, then your transformation that expresses the compilation to the underlying code will become very complex. So it's actually for keeping it simple reasons that we compile to bytecode, and it's also why we use closures, because every AST node in our transformation language can be translated to exactly one closure all the time. So our compiler is, in that sense, really simple, and that's what we wanted to keep, simple compilation. I don't know if it answers it enough.
Okay, any questions? I have one last question, if I may. What you've done reminds me, or it's analogous to the common language framework of .NET to a certain extent.
Yes.
And what that allows is that, if you've got managed code, so C# and J sharp and so on, you can actually call libraries in one language from another language. Can you see something like that happening here? So you can actually call rules in one transformation language in another transformation language. Or is the semantics of the transformation language? At the moment, I can't imagine how I could mix a graph-based transformation language with a...
For example, I can give you an example in which this will already work. In ATL, you can define helper attributes, which are actually derived properties on your model that aren't there in the original meta model, and they're basically overlaid by the VM. And when I try to, I'm going to go back a bit here, when I try to evaluate something like this here, the source property, that source property could actually be defined in a model, but for interoperability reasons, that could also be an ATL attribute helper. And there's actually an OCL expression behind that that then gets evaluated. So that's a transparent case of where these just interact. It's actually really hard to prevent them from interacting. So.
Okay, so thank you very much.
Thank you.